the normal model, and it was so important that that chapter was the entire unit itself, because we had to make sure that you understood what the z-score, how that works, how to get the area, the language of the normal curve, and all that kind of stuff. Sampling distribution is the same. So it's very important when we go through this that you understand the vocabulary, you understand the way things are notated and written, and what all those things mean. So I take you step by step through that during this chapter. You will end up testing this chapter. Actually, it'll quiz next Monday, and then the test over just chapter 18 is next Wednesday. Okay, so that's kind of the long-range plans. And so let's start with your chapter 18 notes, part 1. Okay, so here we go. First thing is this vocabulary, these words called sampling distribution. So whenever we have this distribution of the sampling distribution, basically this is meaning a collection of samples and how they are placed, you know, in relationship to each other, how they fall. If you were to make a histogram of the data, what shape it would take on. Okay, so we're going to see throughout this chapter that we're going to address how we can get it to be normally shaped. That's critical. We're going to do z-scores and use standard deviations and all that kind of stuff, then we have to have a normal, uniform, or unimodal and symmetric shape. Okay. So in these distributions, we have sample proportions, which is what we're going to do with our M&Ms today. We're going to get the proportion of blue M&Ms and the proportion of orange M&Ms in your sample. You also can get sample means. Sample means would be something like if every day this school year you ran a mile and you recorded the times, and then by the end of the year we took an average of those times. So then that would be your sample of 1 mile runs. Okay. So the whole idea of sampling in general, the whole reason you get a sample is because you want to learn something about the entire population just from one sample. You know, to me that's mind-blowing that we can have enough validity in numbers that we can take one sample, and from that one sample we are going to attempt to infer something about the population of interest. Okay, well, in order to do that, there's some critical things that must happen. If you do a poor job of sampling, then you might have bias. You may have something that's unrepresentative, and those would be reasons to totally throw out your data. That's why the very first thing that we talked about this year is getting a representative sample, because without that, you just forget it, everything else. Okay. So, the pattern that gets displayed, because there is variation from sample to sample. So, let's think about this. In a minute, when I give you guys all your sample of M&Ms, are you all going to end up with the same proportion of blue M&Ms and the same proportion of orange?
Yes.
Yes? Okay. I would be very surprised. No. Some of you are going to have a little more than average, a little less than average. You know, we may have more in the center, or, what's expected. That is sampling variability, because from sample to sample, there is variability. The question is, how much can it vary to be reasonable? And what's your answer to that? How much can your sample vary from, say, what's expected to be reasonable? Good. That's 2 standard deviations. So then the next question is, how big is the standard deviation? So that way I know how many percentage points off it can be, and so on. So that's where we're headed. So, because there's variability, we end up, though, having all of those things lay out in a long-term pattern. It will land in a pattern. Now, notation-wise, we are going to reference our sample proportions as this thing called p hat. Okay? So your sample proportion is this p hat. And I'm sure that you can understand that you cannot use one person's p hat to estimate the entire population proportion. And that is represented by a plain letter P, is the population proportion. Okay? So you should understand, one person's sample cannot then be my die-hard estimate of the population proportion. However, it can reasonably give an idea. It can give an estimate within a certain distance of the sample. Okay, so your sample proportion should be able to give us a reasonable kind of general location of where the data falls. All right, so let's consider the way the information falls is generally in a normal curve, and we'll talk about that more later this week. But let's draw this. This is a sampling, because we always want to label our distributions, a sampling distribution of sample proportions. Okay. And so what's going to happen is there will be a natural placement where, there's one person's sample results, a proportion of whatever, and then, maybe most people are getting that particular proportion. Some get a little higher, okay, or maybe even a little higher than that. Some get less than what was expected, and some get even less than that. But the bottom line is that all of these samples will form this shape, which we're going to talk about later this week of how that lands in the normal distribution. Okay. The last thing to talk about before we actually get into counting our M&Ms is to talk about what is this value right here, and what is the size of this standard deviation. Okay? Well, we're going to learn this week that sampling distributions have particular rules. They have, this is the formula for where the mean of the sampling distribution falls. In fact, I want you to understand how to read these letters. This, of course, is the mean. And then this p hat is meaning we are going to tell you that the mean of the sampling distribution of sample proportions. Okay. And what we are told is that that equals P. And what does P represent? That true population proportion. So if the M&M company says they put out 24% blue M&Ms, then guess what? The average placement of all of my samples of my students is going to be 24% blue, what they got in their sample. Okay, so that's what that's saying. Then this here gives me idea. This says that the standard deviation of the, see, here we go, got that right there, that p hat, the sampling distribution of sample proportions is this formula, and I'm not going to write out what that is, but I am going to really draw your attention to the fact that the letter that is used in this formula is the true population proportion. Do not put your p hat in this formula. Your sample results do not go here. This p is like what the M&M's company claims. They say they put out 24% blue M&Ms. So that's what goes there. That P is 24% in that particular distribution. Okay, so let's put this to action with our M&Ms. I'm going to give you a sample. Each of you are going to get a package. Now, there are more than 50 M&Ms in your package. In fact, the 1.7 ounces, 1.69 ounces in your M&Ms package typically are 54 to 57 M&Ms. Now I want you to take out 50 of them. I do not want you to dump them all at one time and then pick your favorite 50, even if that's unconscious, you know, that could have some bias to it. You know, we're going to be looking for blues and oranges, so maybe you end up picking all of those and leave. So I want you to tear your package and count out 50 so that you are not having any bias in the 50 that get chosen into your sample. All right, and then in each pile, you're going to then tell me the number of blue M&Ms you have. That's what I had. And then put them as a proportion. So 12 over 50 would mean I had 24% blue M&Ms. And so on. And then do the same for counting your orange. Once you have counted, then you can eat your M&Ms. Let's actually fill in the numbers and your sample results. Okay, so we'll do the blue completely through. We won't do the orange completely through. So, first things first. What number goes right here at the mean of this distribution? 24%. And the reason that this is 24% is because that's what the Mars Candy Company says that they make. 24% of all of the M&Ms that goes off their assembly line are blue M&Ms. And you see this right here? The mean of the sampling distributions of all samples of size 50 should be the 24% that they claim is what they produce. Okay, yes?
Do you not change that to equal, like, number the n?
Ah, that's a good question. This is a distribution of proportions. I'm going to put all the proportions in here, not the actual number. So this is a proportions distribution. So I have proportions in here. Okay, good question. So let's figure out what the sampling distribution or the standard deviation is. So we can see what number did you get of your proportion of blue, and is it weird? Is it more than 2 standard deviations out? So let's figure this out. So the standard deviation of our sampling distribution of samples of size 50 are going to have, what numbers do I put in here for P? Yeah, that's 0.24. That is not what you got. It's the population claim divided by N, which is 50. The sample size is what N represents. Okay? So that number is 0.0603. So for simplicity's sake, I'm going to say 6%. So let's draw in our other numbers here. So our other numbers, we got 30%, 36%. Okay, so put those in down below. We go to 18%, 12%. So, who has, or if you have, what proportion of blues are you considered an outlier? Okay, below 12% blue, and what else? Above 36% blue. Now, just for this one, I want to see how this particular class distributed their data. Okay, so I'm going to go around the room and ask you what your proportion of blue is, and I'm going to write it in here. Okay, so, all right. Now, this isn't completely normal. I mean, we need to collect more than just what we have, but I guarantee you that over the course of today, and I wish I had written down all of today's information, but it would fall normally around the true proportion. Now, let's examine this little guy right here. This was our little 44% person, which we would consider that's our only outlier. This one is the only one that was more than 2 standard deviations away. So let's actually figure out what is the probability that you get a sample proportion greater than or equal to 44%. Okay, let's figure out that answer right now. So we can see how likely was it to get this little random sample here. Okay, and so look at how this notation is. It's important that you understand what this writing means. What's the probability that you get a sample proportion greater than or equal to 44%? So that means I want to figure out in this little shaded area to get that and above. How do I do that? Not 1 minus, well, I guess I could 1 minus, but still need to go a particular direction with this. Z-score. Correct. So we need to see how many standard deviations 44% is above what was expected. So the z-score is, and do these in decimals, 0.44 minus 0.24 over our standard deviation of 0.0603. So let's see how many standard deviations that was away. Do that really fast. Okay, so I got 3.32 standard deviations away. So we are 3.32 standard deviations up. How do I now figure out the probability?
Norm CDF.
Okay, so let's norm CDF. Now, you need to be aware that on your paper, you do not have to write the calculator speak. Like, you do not have to write out norm CDF from 3.32, 99. Now, I will frequently do that on my answer keys because I want you to see how I got my answer. But here is how you write your answer. In this case, the probability that a proportion is greater than or a sample is greater than or equal to 44% is, and then I go do that answer. Is it 3.32? Wow. 0.00045. So 0.045% chance that we would have gotten 44% blue or more. Now, the most important thing is what your brain can infer from this. And here it is. Ready? Here's the ultimate summary of everything in this chapter and then leads us into the whole entire semester. Here it is. All of these people right here, you got something within 2 standard deviations of what was expected. All of these people right here do not have evidence that the M&M company's claim is wrong. Okay? All of these people in here do not have evidence that the M&M company's wrong. So as far as we can say is the proportion of blue M&Ms may be 24%. But guess what? This person here has evidence. This person here got a rare enough sample that is so statistically unlikely to have happened if the M&M company is putting out 24% blue. Then we say, so this was the one package I picked out of the whole smear of boxes of M&Ms that I had today. This happened to be the one I picked out, and I would say, whoa, the M&M company is not putting out 24% blue M&Ms because I got something that was so statistically unlikely that I have evidence to reject this claim and decide that they're putting out something more than 24%. I can't say what it is, but it's more than 24%. Yes? We do, in chapter 21, are going to address what happens if they are putting out 21%, and this just happens to be funky weird, and we make an error in our conclusion. Then that's called a type 1 or a type 2 error, and we talk about that. So that we'll address that. In fact, let's remember, 3 weeks from now, this little sample right here, when we talk about type 1 and type 2 errors, and we'll talk about that. real quickly, let's see how many of you guys had outlier orange proportions. So what is the mean for the sampling distribution for the orange? Okay, 20%. With what standard deviation? The standard deviation for the sampling distribution should be square root of 0.2 times 0.8 over 50. That is 0.056. So if I was to make a normal curve with an average of 0.2, and we would label this proportion of orange M&Ms, it's important that you label these curves. Otherwise, how do I know what this is representing? With n equal 50. Okay, so this is 20%. Actually, I like to write it as percent. Okay, and I want to go these numbers up. This is 25.6%, 31.2%. If I go down, that's 14.4% and 8.8%. So guess what? If you had less than 8.8% or greater than 31.2%, you have an outlier amount of orange, proportion of orange M&Ms. So how many of those do I have? Wow. Well, see, that should go hand in hand. Do you have real low? Okay, what proportion do you have, or what percent? Okay, so we got a 6% proportion. This coincides with the person that had an unusually high number of blue, so that makes a little bit more sense. Okay, what you got over here?
I got 1%.
You can't have 1% because it's out of 50.
I have the data.
No, what? How many M&Ms? Hold on. How many M&Ms do you have? Okay, and true, that's right. How many of them were orange? So hold on, how many were orange? Oh, that's 10%. So yours is right in here. Okay, so you're all right. Okay, what you got, Ben? 8%. Okay. So we did have one right there at 8%. Okay, so we can talk about those. Those are obviously just a little over 2 standard deviations, not quite as rare as the other one we had. So, in summary, how do we tell if our sample results agree with the proportion of blue or orange M&Ms that the company claims that it has? Okay, we're actually just going to kind of answer this differently. So we're going to say this. If our sample results are within 2 standard deviations of the claim, then we do not have evidence to reject the claimed number. And this language may sound a little strange, but it's leading into some of the language that we use later when we do chapters 19 through 22. Okay, boom, that's the end of our M&Ms lab, and the idea of sampling distribution, notation, how to get the new standard deviation. So next, we're going to look at the examples. So go to this page here. This one is for example proportions. We are going to do 2 of these problems. All right, here we go. Hey guys, we gotta do this or else we're gonna run out of time. So here, this is saying the mean of the sampling distribution is whatever the true P is claimed to be. Here is the standard deviation for the sampling distribution. Now, this all right here looks pretty confusing, but let's look closer. It's actually nothing more than what we've already done. When you get a z-score, you are taking your sample, you're seeing how far it is away from the true P, and you're dividing it by the standard deviation of the sampling distribution, which is this formula here. This is nothing more than what we have already done, so don't let all of those symbols give you, freak you out a little bit. So here we go. Number 1. An opinion poll asks a simple random sample of 1,785 adults whether they attended church or synagogue during the past week. Suppose that 60% of the adult population did not attend. What's the probability that the sample proportion of those who did not attend is at least 58%? So let's walk through what each of these things is. What does 1,785 adults represent?
Population.
That is not the population.
No, that's the
That
sample.
is your sample size. They took a sample of 1,785 adults. They asked them if they had attended a church or synagogue this past week. And suppose that 60% of the adult population did not attend. What is that?
That's the mean.
Aha! This is saying 60% of the adult population. That is the P, the true P, which is the mean of the sampling distribution. Okay? Because when it says what's the probability that the sample proportion of those who did not attend is at least 58%, so that's indicating that 58% is representing the P hat, the sample results. All right. Now what else do I need to get here? First of all, I know that I've got 60% happening here. I have a sample at 58%. And my question is, what's the chance that it's at least that? So which way in a picture does that go? Down? No, at least that? Is that much or more? So what I want is this shaded area. That's the probability that my sample could be 58% or higher. So let's do the z-score. 0.58 minus 0.6 over...
You gotta do the standard deviations.
Yep. You gotta come over here and get the standard deviation of the sampling distribution. It's the square root of P 1 minus P over 1785. Okay, now, I want to show you a calculator button that you can push to really help you with some stuff. If you don't know this, then you need to get it figured out right now, or else you're just going to be behind the curve on knowing how to do this. So here we go. Here's my 0.6 times my 0.4, and I get 0.24. Well, when I divide that by 1,785, I get a crazy small number. It's 1.345 times 10 to the negative 4. So that I do not have to type that in, because I don't want to have to be typing 10 to the negative 4th in or whatever. You can do the square root of the previous answer. And you get the previous answer by doing the second button and the negative button. And that's how it'll recall the previous answer. So if you didn't know that, then you're going to want to start using that now. Okay? All right. So when I do that, I get 0.01159. I want 595. I want you to round to 4 decimal places for standard deviations. So what would I do for that? Yep, 0.0116. So 0.0116 is my standard deviation here. So that ends up giving me a z-score of negative 1.7241. So you go to the side and you go run your little calculator moves. But here's how you write your answer. The probability that my sample proportion that I get is greater than or equal to 58%. See, that's what I'm answering. Is, and now I've gone off to the side and I've done this. Okay, but you don't have to show that. And then I got 95.77%. Okay, but this is the way you notate your answer in a big boy way. Okay, yes. I think just because of your parentheses here, that's pretty standard that you're notating the probability of this event happening. Because like, whenever we would do in 8th grade or whatever, probability of blue, you know, so there you go. All right, now Now, we're skipping number 2 and doing number 3. Okay, this is the real deal of how they handle medical research. In fact, there's a whole lot of cancer research happening right now. I know that whenever I look up stuff for my mom, I'm looking up stuff that I look at the date. And if it's older than this year, I pretty much don't even read that article. But I'll go look at that medical journal, and I may not quite understand all the full medical language. I can't look at some of those words and kind of understand it. But I can understand the conclusion that was drawn because I understand the statistics of what they are saying and talking about a p-value and all these different things. So I can understand the conclusion that they're drawing based on my statistical knowledge. So, here we go. So, in 1983, this was quite a ways, 30 years ago, over 30 years ago, so this is old medical news, but back then in 1983, the proportion of blood recipients, so people that got a blood transfusion, they had surgery, they were in a major accident, people that got blood, that got viral hepatitis, even though they were careful in screening, was 7%. Okay, so I personally wouldn't be okay with that. And that was actually published in the American Journal of Medicine in 1983. Suppose that a new treatment is developed, and it is believed to reduce that incident of infecting people with the hepatitis. So this treatment was given to 200 blood recipients, and only 6 of the 200 patients contracted hepatitis. So, of course, 6 out of 200 is 3%. Yeah, I know it's less, but is it an unusual amount less? How do I tell if this is significantly less than the claim? What? I have to figure out my standard deviations. So, then, if this is unusually low, then I can say, statistically, there is no way that this should happen. It's very unlikely that this would happen if 7% was still the case. So if I end up with a really low number, then I'm thinking this 7% infection rate is no longer true. I think now it's actually lower. That's where we're headed with this. That is what medical researchers do. Let's figure it out. In fact, here's the question. Does this result indicate that the true proportion of patients who contract hepatitis after experimental treatment, after this new way of checking the blood, is less than 7%? So, or is it just happening because of sampling variability? Is it just happening because it's within 2 standard deviations and that just happens? All right, let's see. What's 200? Okay, N is 200. The mean of the sampling distribution is 7%. P hat, the data we collected was 6 over 200, which is 3%. Now, the standard deviation for the sampling distribution is that square root of 0.07 times 0.93 over 200. And that number is 0.01804. So now what am I going to be doing? Standard z-score. Z is, see how far 0.03 is away from 0.07 in terms of standard deviations. And it is negative 2.22 standard deviations. So what do you have to say about those results? They are significantly lower. They are statistically unlikely if 7% is good real infection rate still. So I have evidence that implies, I have evidence to infer that with this new treatment, the infection rate is lower than 7% now. Because this should not have happened, statistically unlikely. So here's how you write your conclusion. It would say something like this. There is evidence that the infection rate is less than 7% for the new treatment. Good. Since my sample was more than 2 standard deviations below 7%. Boom. Okay? Important concept. Alright, we are almost done. We just have to take you through means instead of proportions. They are almost identical in all their computations. It's just that. So turn the page. We are now dealing with averages of data instead of proportions of data. Okay? So, for example, with this one here, this one actually doesn't have context, but let's say that you ran 64 miles, for the last 64 days you have run a mile. Then every single one of you would come up with your average time to run the mile. Average time to run the mile. Average of 64 times for the mile. See, it's times. So that's why you're getting an average time. It's not a proportion of blue M&Ms. So that's why these are means, because it's an average time for your 64. Plus it says, what's the sample mean? So do you see how this is a distribution filled with means in it instead of proportions of blue M&Ms?
So the actual numbers?
It's a value of time, yes. It's an amount of time. Yes. All right, so here n is 64. The mean for the standard deviation is the mean. Oh, at 2:05 we're having a fire drill. Okay? And they say that is 30. Here's the deal. Look here. The standard deviation for the sampling distribution of means has this formula here. Do you see this one right here? See this? It says standard deviation for the sampling distribution is the mean of the population divided by the square root of n. So here they tell me that the mean of the population is 4. So I have to say the mean of the population divided by the square root of n. So that's 4 divided by the square root of 64. So that's 4 over 8. So that is 1/2. Now, let's look at the question. Find the probability that the sample mean, that's how you notate your sample mean, is 31. And the question is, find the probability that the sample mean is greater than 31. That's the question we are answering. So, keep in mind, we have these means in here. They'll be mostly around 30. But then, how far is 31 above? That's 2 standard deviations since the standard deviation is 1/2. So I'm going to norm CDF from 2 to 99, and that number is 2.28%. Kind of went through that pretty quickly. It's just a slight different notation because it's means instead of proportions, but the overall idea is the same. Okay, questions on that? I think I have a couple minutes. I have a couple minutes that I want to go over this one with you. Oh, actually, if I run out of time, let me tell you about your homework. Your homework is just 8 of these problems. The first thing you identify on your homework is whether you are dealing with a mean or a proportion. Okay, so for example, this first one, it's a sample with a mean of 19.2. So this is probably what kind of problem? A mean problem. Now look, I want you to go show your work on the next page. So problem number 1 is a mean problem. And then I just have a little template to make sure you're showing all the data. So this homework assignment seems pretty thick, but it's only 8 of these problems, and we've done that many in class, so you're going to be good. All right. Real quick quickly, you may not even have time to write this down, but I want to walk through this one real fast. This says a person who rides the elevator. So this is a person that rides the elevator, averages 148 pounds. Okay, but guess what? We're going to be talking about 32 passengers in an elevator. So I don't want the mean and standard deviation for one passenger. I need to find the mean when 32 passengers ride the elevator. So the mean for 32 passengers is going to be 148 pounds times 32, which is 4,736. Okay, how about the standard deviation of 32 passengers? How do I get that? Is standard deviation also affected by multiplication or not? Yes, standard deviation is affected by multiplication. So this means that standard deviation for 32 passengers is 486.4 pounds. Now let's do the sampling distribution. The mean for the sampling distribution is the same mean as the population. The standard deviation for the sampling distribution is this formula, which means 486.4 divided by the square root of 32. And that is 85.98 pounds. Well, guess what? What's the probability that when 32 passengers ride the elevator, they will have a weight of 5,000 or more? Because that's the limit. So 5,000 minus the 4736 over the 8598 is a z-score of 3.07, so that's good. It's not likely to be going over the limit. So the probability that I'm going to get a sample of 32 people that is greater than 5,000, okay, you guys can go ahead and go, is this small, 0.107%. Yay, so they'll probably all live.
That's good.